somewhere in 2008. So there's quite some work to be done. And what's also interesting here, you have different constellations. You might have high data rates with short range. You might also trade off bandwidth for range. So you might be somewhere here. And the communication class with the longest range, about 1 kilometer, using a directed antenna is reserved for emergency vehicles. So emergency vehicles are planned to actually be able to notify one-hop cars up to 1 kilometer ahead. Now the other component that's important here is routing. So when you cannot reach the other cars directly, you do it multi-hop. And in that way, vehicular ad hoc networks are some special flavor of generic ad hoc networks. You might have heard of mesh networks, wireless sensor networks, which are some form of either static or dynamic multi-hop networks. There are other application areas for ad hoc networks, and one of the most promising areas of this technology that is around now for almost 10 years are vehicular networks. Whereas in these, or for most of these other networks, you use topology-based routing, where the nodes try to discover the logical topology of nodes and then build routes based on that knowledge. In vehicular networks, you do it a little bit differently. Let me give you an example. If you want to implement this road condition warning applications I spoke of earlier, you can do something like you have this car detecting the icy road, and then it sends a message to that car, and this message sends it to that car, and so on. And these cars get a display, icy road ahead, drive careful. That's essentially it. Sorry? Okay. And if you look at these scenarios, you find that they're a little bit different from what is looked at in generic ad hoc networks. You have very dynamic network topologies, simply because cars drive fast. So your topology changes all of the time, much faster than, for example, if you have networks consisting of pedestrians, or if you think of mesh networks, it's relatively rare that houses move, so you have nearly no mobility in there at all. Next thing is, whereas, for example, pedestrians move in a rather uncoordinated way, cars are usually bound to streets, so you have very different movement patterns that makes different classes of routing necessary. One problem that you don't have in cars is, for example, energy constraints. Normally with mobile devices, you don't want to waste too much energy because this would drain the batteries too fast. In a car, this is usually no problem because the car generates its energy constantly on its own. So there's a quite different setting here. There's another thing that's different. In normal networks, you have addressing modes like unicast, multicast, broadcast, and so on. You want to send messages to single nodes, or to a group of nodes, or to all nodes. That's essentially it. Any cast could be added. When it comes to vehicular networks, you usually don't want to send messages to a specific node, but with all these warning messages, with all these e-safety applications, you want to have some kind of position-based addressing. You want to send this warning to all cars approaching your current position, to all cars driving on the same street, or to a car that drives 5 kilometers ahead of you to request some information about traffic status. And this leads to new forms of addressing, like geo-broadcast. You want to send, for example, if there's an accident here, the cars here want to send messages to all other cars within the next 3 kilometers coming up this road. Or geo-anycast, you want to send it to simply one car in this area. And this has led to the development of new forms of routing protocols, so-called position-based routing. One incarnation was found in the so-called FleetNet project, that was done by Daimler Chrysler and others in, I think, up to 2003 or so. And they have two operation modes of this routing. When you are yourself inside this area, you can do some kind of controlled flooding. You just send the message to all neighbors, and the neighbors forward it if they are themselves within that area. So you simply flood an area. That's quite trivial. When you're not part of this area, for example, your car that's still 5 kilometers before that, and you want to send a message to that, you need an additional step, additional to flooding. You need to, some kind of line forwarding to forward that packet into that area. And the special incarnation of this protocol in the FleetNet project was called Cached Greedy Geocast. This line forwarding mode works like follows. You specify a destination area where you want your packet to be delivered to. And another assumption is that each node constantly measures its position by ways of GPS or whatever, and periodically broadcasts this information to all of its neighbors. This process is called beaconing. So each node knows its own position and the position of all neighbors. And when it receives a packet that is destined to some remote area, it simply makes a routing decision based on these positions and tries to bring the packet nearer to the destination area. So, for example, here, if A wants to send a packet to that area here, it looks at its neighbor table, it sees there's B and C. C is obviously closer to this area than B, so it sends the packet to C. C might send it to D and then to E, and then this area is reached, so you have this path without any topology information. You just really look at the geographic positions here. This principle is also called greedy forwarding because you don't make any clever calculations. You just greedily forward it nearer to the destination, and that's it. There might be different strategies how to be, what actually means closest to the destination. This depends on if you really want to get to have routes with as few hops as possible, or if you want to have to preserve energy and have routes where you send, for example, only on short links and so on. But I think for time reasons I will skip that. There are other problems when it comes to local maximum or local maxima when the message reaches this node here and should go from S to D. For that node, there's no nearer neighbor, so you need some strategy to get out of this local maximum. Different possibilities. You can try to get in a special parameter mode, no perimeter mode, that's wrong here, and try to use something like left-hand rule or so where you send it, or you can simply say, okay, cache it and wait for mobility to resolve this local maximum. And research has shown that this kind of position-based routing actually has a lot of advantages in vehicular networks. It naturally fits the way of addressing when you want to send packets to certain areas. And it also scales very well. So you have here some examples. You have simulations, and you see here the packet delivery ratio. And this line here is a specific topology-based protocol used in ad hoc networks named DSR. And you see when you have a larger area and vehicles are farther away, this packet delivery ratio here, almost all packets get delivered, but then it declines quickly. And at the same time, position-based routing is able to maintain almost 100% delivery ratio. So, and also the amount, the overhead created by the routing process, by the routing protocol, goes up very quickly with DSR, but remains relatively small with position-based routing. So there are quite a lot of reasons why you want to have this position-based routing, and there's quite some consensus that this will be the kind of routing in vehicular networks. There are some drawbacks. You need a GPS, but you assume that future cars all will have navigation systems anyway, so this isn't really a problem. And there's a problem if you want unicast addressing. If you want to send a packet to a certain address, you first have to find out in what area that address is before you can deliver it. So you need some additional location service which creates additional overhead. So for unicast routing, it's not really perfect, but it is assumed that most of the applications don't need unicast routing anyway. I also have some ideas, but they are not really major to combine topology-based and precision-based routing. Anyway, yeah, but as we're here on a security conference, I also wanted to have some words regarding security and privacy. You remember these slides from the beginning of my presentations. Vehicular communications seems to offer a lot of nice applications, a lot of opportunities for safer roads, where you can warn drivers for more efficient driving, for more fun while driving, and for easier maintenance. So it looks very promising here. Now, I probably assume at least 90% of you already has some ideas what else could be done with such networks. Will there really be safer roads if something like that can happen? Of course, I can just use my notebook. Either I have I have a software radio, or I might be able to buy such 802.11p equipment anyway, and I just send warning messages, and then cars start to brake without any reason. Might not be so good. And more efficient driving, yeah, sure, but the question is for whom? I mean, if there's such a system, what I would do is I would send a lot of traffic update messages to this traffic operations center and say, hey, at this location, or at this location here, there's a traffic jam. And then this traffic operations center would disseminate this information to other cars, and they would all use an alternate route, and then the route would be free for me. Would be very nice to have something like that available when you're a little bit in a hurry. Yeah, or could be interesting to see how drivers react if you send fake messages. Hey, there's a message from the silver car behind you, and this tells you you're an idiot. Could be that this leads to some interesting reactions of the driver here. Another problem is with privacy. If the cars start to send position beacons all the time, giving their identity and their position, people could try to track this information. Think, for example, of McDonald's or whoever, or some oil companies. They have a lot of stations around, and if they all have access points and simply collect these beacons, you can get a pretty fine picture of where are people driving when. And people give this information out for free. Yeah, and there could be a lot of more problems arising if you have such a system built in an insecure way. So, for example, think of software update. If I make it somehow to send false or faked software to a car, and the car actually starts using that software, it might be in the garage a lot faster than necessary. And I'm working in a project that actually deals with the security aspects and the privacy aspects of these vehicular communications. And for us, the first year now is over, and we spent most of the time of this first year looking into problems and attacks and threats, and find quite a lot of evidence that security is really needed here. So there could be, for example, attacks where cars try to modify the position they report in their beacons. So this car could send beacons telling everyone, hey, I'm here. And this could be used for black hole routing and for rerouting data, intercept data. I'm coming back to this on the next slide. And cars could even go further and send beacons for virtual identities. So they can do a so-called Sybil attack, where they create virtual presences or virtual copies of itself at different locations, and by that they might be able to control all the traffic that goes along a route. Or they might impersonate other nodes and discredit